Hello chemistry students, this is Mr. Laudermith. Because I'm not in class today, I wanted to make this screencast to show you at least how to start Unit 4 Worksheet 3. This is really the last new activity we're going to be doing prior to the big quiz on Monday, and it covers the last learning target, which involves using percent composition and ratios of masses to figure out the formulas of compounds. So we're going to go through the first example together, which involves compounds of carbon and oxygen. And we're told in the instructions, use the following information about the masses of each element in each pair of compounds to help you suggest formulas that account for these ratios. So we're given carbon and we're given oxygen. We have one compound that contains 57.1 grams of oxygen and 42.9 grams of carbon. And then we have a second compound, compound B, which contains 72.7 grams of oxygen and 27.3 grams of carbon. Now remember, this is not or shouldn't be entirely surprising based on what we added to our story so far. We know from the work of people like Lavoisier and Dalton that you can have elements combining in multiple ratios. They don't always have to combine in the same ratio, but they do have to combine in whole number ratios. So the fact that we can have two different compounds of carbon and oxygen really shouldn't come as too big a surprise. The first thing we're asked to do is to determine the value of the ratio mass of oxygen divided by mass of carbon in each compound. So we right now need to do this. So you might want to pull out your calculator to verify that my math is correct. You'll need a calculator for the rest of the worksheet, but I'll show you how to do this. So for compound A, we've got 57.1 grams oxygen, 42.9 grams carbon, and if you type those into your calculator and divide, you get a ratio, if we round to 2 decimal places, of 1.33. So A, our ratio of oxygen to carbon, we'll call it 1.33. For part B, or I should say compound B, we have 72.7 grams oxygen, 27.3 grams carbon. When we divide that, we get a ratio of about 2.67. Again, I'm just rounding to 2 decimal places. So compound B, ratio 2.67. The next question, how does the mass ratio for compound B compare to that of compound A? Well, you might notice right away, B is bigger than A. B is bigger than A, but we can also, I think, go a step farther than that. You might notice that 2.67 is about twice as big as 1.33. So I think we want to be as specific as possible, and we can say the ratio in B is twice as big as the ratio in A. All right, how does that impact the possible formula for these compounds? Well, we don't know yet. We're getting there. C says express these ratios as improper fractions. Here is where you might have to reach back to maybe middle school math. Might have been a while since you've talked about improper fractions. Say, for instance, that I have a number like, let's do 3.5. I can express 3.5 a couple different ways. I can express 3.5 as a mixed number. That would be 3 1/2. Or I can express it as an improper fraction. An improper fraction means I have just a numerator and a denominator, So just a number on top and a number on bottom, and the number on top will be bigger. So 3½ is the same thing as 7/2, or 7/2. And you can verify that in your calculator. In case you're wondering, how did I know it would be 7/2? Looking at this mixed number, 3½ I knew that the numerator would be the 3 times the 2 plus the 1 that was left over. 3 times 2 is 6, plus 1 is 7. And then I just had to take that 7 and put it on top of the 2 from the fraction. So 7/2. So in this case, for A, my ratio was 1.33. Well, you might immediately say, oh, 0.33, that's 1/3. So that's going to be equal to 1 and 1/3, which is the same as an improper fraction of 4/3, 4/3. For B, I had a ratio of 2.67. 2.67, well, so that is 2 and 0.67, that's the same thing as 2/3. So I've got a mixed number of 2 and 2/3, which is an improper fraction. If I do the 3 times the 2, I get 6, plus the 2 is 8. I stick it over the 3, it is 8/3, 8/3. So as an improper fraction, A was 4/3 and B was 8/3. Notice something. B is still twice as big as A, because if I take 4/3 and I multiply that by 2, I get 8/3. So I haven't changed the comparison at all. B is still twice as big as A. I've just changed them into fractions. For part D, it says, for each hypothesis, sketch particle pictures for the compounds of A and B that account for these mass ratios. Write the formula for the compound in each diagram. Hypothesis number 1 says, atoms of carbon and oxygen have the same mass. Okay, that's pretty easy. If atoms of carbon and oxygen have the same mass, all I need to look at is my ratio. For A, the ratio was 4/3, but remember what that was originally. If I go back all the way to the top here, I got that by doing mass oxygen divided by mass carbon. So when I say the ratio is 4/3, what I'm really saying is it's 4 oxygens for every 3 carbons. Okay, I can draw that. 4 oxygens and 3 carbons. There's my 4 oxygen atoms. And there's my 3 carbon atoms. Now, is that really how that would be put together? I don't know, but it matches my ratio. I said I needed 4 oxygens and I needed 3 carbons, so I just made a compound that had those atoms. And if I had to write a formula for that, I could write it as C3O4. 3 carbons, 4 oxygens. Okay, what about for B? Well, B, I had a ratio of 8/3, but again, what I'm really saying is 8 oxygens for every 3 carbons, because that's how I did the math, oxygen divided by carbon. Well, okay, I can draw that one. Maybe this time I'll do this. I'll do 4 oxygens. 3 carbons, and 4 oxygens. Okay, and that formula, well, to follow the pattern I did in box A, would still be C3, but now it is O8. Okay, so again, those are formulas and pictures of the compounds, assuming that carbon and oxygen has the same mass. That the mass of one oxygen is equal to the mass of one carbon. Hypothesis 2, though, says atoms of oxygen are heavier than carbon atoms by the ratio in compound A. And that part there is kind of key. In compound A. Well, let's consider that for a second. This time, I'm saying that the oxygen has a mass of 1.33 compared to the carbon, which has a mass of 1. Where did I get those numbers from? Well, that was the ratio I calculated. When I did oxygen divided by carbon, I got a mass ratio of 1.33. So I'm saying that if the carbon is a mass of 1, then the oxygen is heavier with a mass of 1.33. Okay, how could I show that in a picture? Well, let me draw a carbon atom. And I know my oxygen is heavier, so I can make it bigger. There's oxygen. So there's carbon and oxygen. And in this case, I have a ratio of, well, I have just 1 carbon and 1 oxygen atom. So my formula would simply be CO. So the difference between hypothesis 1 and hypothesis 2, I'm just saying that the atoms are different sizes. They are different masses. Well, how will that affect B? For B, I still have carbon. I still have carbon with a mass of 1. And here's where you might say, oh, well then oxygen has a mass of 2.67, right? No, because we were told, assume for hypothesis 2 that oxygen is heavier than carbon by the ratio in A. So we're going to keep the masses the same. We're still going to say that oxygen has a mass of 1.33. But wait a second. Oxygen and carbon, we're keeping the masses of the atoms the same, and yet when we actually did the ratio, we said we got a ratio of 2.67. Hey, I have an idea though. If the ratio is 2.67, that would mean 2.67 oxygen and 1 carbon. And notice something. 2.67 is the same thing as 2 times 1.33. So this time, I need to draw a picture that has 1 carbon atom and 2 oxygens, because that's what my mass ratio shows. I still have a carbon at 1.00, but my oxygen is now 2.67. That's twice what it was in A, so I must have twice the number of oxygen atoms. So I had 1 before, now I'll have 2. So if I draw my particle picture here, I know I'm starting to run out of room. I'll have my carbon, and I'll put a bigger oxygen, one on each side. That matches my ratio for hypothesis 2. I have 2.67, 1.33 plus 1.33 from the oxygen, and just the 1 from the carbon. So that formula would be CO2. So here we have some possible hypotheses for what the formulas of these compounds are. We don't know yet which of these, if any of these, are right, but this is at least using the data that we have, the mass data, to figure out some possible particle pictures of the compounds and some of their possible formulas. Please continue using this process to answer the rest of the questions in Worksheet 3, and I will see you tomorrow.